Obtain Fourier series expansion for the function f of x equals e raised to minus x, for which x belongs to 0 to 2 pi, where f of x is 2 pi periodic function. Since we have from the general interval x belongs to c, comma c plus 2l, c equals 0 here and c plus 2l equals 2 pi, we have 2l equals 2 pi, from which we will obtain l equals pi. Therefore, we have Fourier series expansion for f of x equals e raised to minus x written as a naught by 2 summation n ranges from 1 to infinity a n cos n x plus b n sin n x. In the general formula, we had a n cos pi n x by l plus b n sin pi n x by l. We replaced l by pi and thus we obtained summation n ranges from 1 to infinity a n cos n x plus b n sin n x. We have a naught evaluated using the formula 1 by pi integral 0 to 2 pi f of x dx, where f of x equals e raised to minus x. We have integral 0 to 2 pi e raised to minus x dx becomes e raised to minus x divided by minus 1, to which we will give the limits 0 and 2 pi. We can take outside the minus sign which appears in the denominator after integration. Thus we have minus 1 by pi which can be taken outside as constant. On application of upper and lower limits to the function e raised to minus x, we will obtain e raised to minus 2 pi minus e raised to 0, where e raised to 0 equals 1. Thus we have a naught equals 1 minus e raised to minus 2 pi divided by pi. We can evaluate a n using the formula a n equals 1 by pi integral 0 to 2 pi f of x cos n x dx, where f of x equals e raised to minus x. Thus we will obtain a n equals 1 by pi integral 0 to 2 pi e raised to minus x cos n x dx. We have the standard formula integral e raised to ax cos bx dx equals e raised to ax divided by a square plus b square multiplied to a cos bx plus b sin bx. Here we have from this integral a equals minus 1 and b equals n. Thus using this standard formula we have integral e raised to minus x cos nx dx equals e raised to minus x divided by 1 plus n square multiplied to minus cos nx plus n sin nx. We have just replaced a wherever it appears using minus 1 and b wherever it appears using n. Thus we obtained this expression. To this expression, when you give upper and lower limit, we have sin n 2 pi becomes 0 and sin 0 is also 0. Thus this term disappears. When you give upper limit and lower limit to e raised to minus x divided by 1 plus n square multiplied to minus cos nx, we will get, giving x equals 2 pi, e raised to minus 2 pi divided by 1 plus n square multiplied to minus 1. This is because cos n 2 pi equals 1. When you give x equals 0, you will get e raised to minus 0 divided by 1 plus n square multiplied to minus 1 into cos 0. We have e raised to negative 0 equals e raised to 0 equals 1 and negative cos 0 equals negative 1. We have minus into minus becoming plus and thus we will get 1 by 1 plus n square and minus 1 into e raised to minus 2 pi divided by 1 plus n square gives minus e raised to minus 2 pi divided by 1 plus n square. Denominator 1 plus n square can be taken outside and thus we will get this expression for a n. Similarly, we can evaluate bn using the standard formula bn equals 1 by pi integral 0 to 2 pi f of x sin nx dx, where f of x equals e raised to minus x. In order to integrate this expression, we will make use of this standard result. Integral e raised to ax sin bx dx equals e raised to ax divided by a square plus b square multiplied to a sin bx minus b cos bx. Here we have a equals minus 1 and b equals n. Hence, this expression can be rewritten as e raised to minus x divided by 1 plus n square multiplied to minus sin nx minus n cos nx. When you give upper and lower limit to the term minus sin nx, it will become 0. We have similar calculations here as discussed previously and thus we will get bn equals 1 minus e raised to minus 2 pi divided by pi multiplied to n by n square plus 1. Having obtained a naught, a n and b n, we can write Fourier series representation for f of x equals e raised to minus x written as a naught by 2 plus summation n ranges from 1 to infinity an cos nx plus bn sin nx, where we have obtained a naught by 2 as 1 minus e raised to minus 2 pi divided by 2 pi. An and bn were obtained in this expression. Notice that 1 minus e raised to minus 2 pi divided by pi is common to every term in the RHS, and it can be taken common from outside each terms in the RHS. Thus we have RHS rewritten in this way, giving special indices n equals 1, 2, etc. for both these functions. When this expression is taken common from this term, we are left out with 1 by 2. Giving n equals 1 to this expression cos nx divided by 1 plus n square, you will get cos x divided by 2. Giving n equals 2 to the expression cos nx divided by 1 plus n square, you will get cos 2x divided by 5, and so on. When you give n equals 1 to this expression sin nx multiplied to n divided by n square plus 1, you will get sin x divided by 2. When you give n equals 2 to this expression n sin nx divided by n square plus 1, you will get 2 by 5 times sin 2x, and so on. This is the Fourier series expansion obtained for the given function f of x equals e raised to minus x, involving both sine series as well as cosine series.